Hi, guys. This is Lesson 5.2. It's all about earthquakes. So, today we're going to learn about the causes of earthquakes, the effects that they have, and especially how seismologists learn to detect exactly where the epicenter of an earthquake was, as well as how they talk about how big the earthquake was, its magnitude. Okay, so think for a second. Where do earthquakes occur? How often do they occur? We've had earthquakes here in Ottawa and even fairly recently, but they're pretty minor. You barely feel them. For the most part, earthquakes tend to occur in this pattern. Take a good look at this. This is global earthquakes from 2000 to 2008 that were large in magnitude, above a 5 on the Richter scale. So when we look at these, this pattern should look pretty familiar to you, especially if you look over here. What you're seeing is that earthquakes tend to follow the plate boundaries. There's a ton of earthquakes right down the center of the Atlantic on the Mid-Atlantic Ridge. There's tons of earthquakes where these plates meet at the border of South America. There's tons of earthquakes around the Ring of Fire in the same place you see volcanoes. We're over here, and you do get some minor earthquakes. And we'll talk about the reason, our local geology, that causes these minor earthquakes as well at some point. Okay, so we see earthquakes in a pattern that resembles the plate boundaries. Well, the causes of earthquakes they can be really different. Earthquakes occur because there's volcanoes. Earthquakes can occur if a cave collapses underground. Earthquakes can occur because a meteor hits the earth or an asteroid, and that shock will cause an earthquake. But the major cause of earthquakes is strain that occurs because of the movement of plates, tectonic plates. And that's why we see all these earthquakes at plate boundaries. And these earthquakes are really just a shaking, a vibration of the Earth's crust that's caused by a rapid release of energy. And they occur at different kinds of faults. The cause of most major earthquakes is the strain, so the tension that builds up along faults or near boundaries between plates. A fault is what we call a break in the lithosphere, a break in the crust where movement has occurred. And we actually have three different kinds of faults that we talk about. We have them at divergent plate boundaries, where you've got two plates that are pulling apart. An example of this one would be like the Mid-Atlantic Ridge. Then we have them at convergent plate boundaries, where one plate is moving underneath the other. It's being subducted underneath. You end up with like those volcanic arcs, those island arc chains. Or another example would be where there's a plate moving under South America. The third kind of fault is what we call transform faults. And these don't have one plate moving under the other. Instead, they're sliding side by side. And tension will build up. There's a lot of friction between these two plates. They don't slide smoothly. Tension builds up, and then it's released, bam, all of a sudden. And that's what causes the earthquake. The San Andreas Fault that you've probably heard of in Southern California, Los Angeles area, is an example of a transform fault. Okay, before we go any further, I'm going to stop for some storytelling. So this is Idaho. In the last lesson, you should have researched the Yellowstone supervolcano. So here's Yellowstone in Wyoming, right over here. In Idaho, right nearby, the state next door, there's a place called Craters of the Moon National Park. And this place is pretty crazy. It literally looks like the surface of the moon. There's been recent, in geologic terms, volcanic activity there. So recent that you don't see vegetation growing back yet. Instead, it really does look like these massive lava deposits. So my husband and I, we were traveling from British Columbia, just north of Idaho. We traveled through here. We did some rock climbing in the beautiful mountains. of Idaho, highly recommended. And then we stopped and checked out this Craters of the Moon. So super interesting place, if a bit disturbing. It looks really dark and desolate. And from there, we started moving north. So there's like a desolate highway that comes through these two ranges of mountains here. So we were driving back north through this area, and there's a sign on the side of the road that pointed, to some geologic thing that we should go check out, maybe 10 kilometers off the road. And of course, because it's me, I had to go look at the geologic wonder. So we drive down the road, and as you're approaching, you can see this weird kind of strip through the hillside, and it's really visible, and it goes on for as far as the eye can see, both kind of north and south. And you couldn't quite tell why that strip of vegetation would be there, or that's missing vegetation would be there. So finally, we got close, and there's these signs describing what happened there. So this region had felt Idaho's largest earthquake in the early 80s, 1983. It was about a 6.9 on the Richter scale, which is a massive, massive earthquake. And this scar that you see on the hillside actually continues for 34 kilometers. It's a 9-foot tall scar where where one chunk fell below the other. So there was a massive earthquake, some massive slippage along this fault line. So this is a visible fault in Idaho. So we got there, we read the sign, and you're looking around, and all of a sudden I felt very uncomfortable standing so close to what was once the site of a massive, massive earthquake. Thankfully, Idaho is pretty remote. There are not a lot of people around there, so there were not a lot of major injuries or anything like that, or property destruction associated with that earthquake. But it left a huge scar on the hillside. So this whole area, even though it's not at what we think of as a plate boundary, this area of Idaho and Yellowstone National Park in Wyoming is really geologically active. Okay, story done. Let's talk about the causes of earthquakes. Well, elastic rebound is the major cause of earthquakes. Here, we've got a fault running between two chunks of the lithosphere. In their original position, you would see this fence being built across there. No one thinks too much about it. But there's always going to be strain if these two chunks of lithosphere are moving in different directions. It's pushing the two chunks in opposite directions. And just like what happens when your sneakers squeak on a sticky gym floor, eventually you get that release of energy. So they will hold tight together, and then bam, eventually it will be released. There's strain, and then finally the strain is released. That release of energy shakes the earth. That's the actual earthquake that you feel. And in the end, there will be displacement. And those two chunks of lithosphere might hang out like that for thousands of years until the strain builds up again and you experience another earthquake. You probably heard people talk about epicenters of earthquakes before. The epicenter is the point on the Earth's surface that's directly above the place that we call the focus, which is where the first movement of the earthquake happens. It's where the earthquake originates, and it's usually really deep within the Earth. Energy is released at the focus and travels away from it in waves, like all energy does. So the focus is below, and the epicenter is the location directly above it on the center of the Earth, or on the surface of the Earth. Okay, pause for a second and think. What type of plate boundaries would have deeper focus earthquakes associated with them? Would it be the divergent plate boundaries or the convergent ones? If you thought that the convergent ones would have deeper focus earthquakes, then you're right. Here we've got an example of a convergent plate boundary. We've got this plate here coming underneath this one. In this kind of scenario, the plate that's moving underneath, there's a lot of tension that builds up here. So this area where you end up with these volcanoes and stuff, there's deeper focus earthquakes because you have more strain going as that plate is pulled underneath the other one. So if we're detecting seismographs, if we want to know exactly where the epicenter was, if we're detecting earthquakes and we want to know exactly where the epicenter was, we use a machine called a seismograph. It really is just like a ball hanging suspended above some paper with some kind of writing implement. When the earth shakes, that writing implement will write on the sheet of paper and show if you have a time recording device on it, it'll show exactly when the shaking started, and the size of the squiggles will show the magnitude of the shaking. We can learn a lot from that. The seismograph records information about the seismic waves, the ones that result from the abrupt release of stored energy at the focus. And there are different kinds of waves. Over here, we've got an example of a seismograph writing on some paper. You can see the squealing. That shows the magnitude of the shaking. And normally these seismographs will be able to record exactly when the shaking started. They also tell you a lot about the type of waves or the type of shaking that happened. There's different types of waves. We have the surface waves. These are the ones that just travel on the outer layer of the earth, and they're the ones that cause the most damage. Then we have the body waves. These are the ones that travel through the earth, and they're divided into two types: primary waves, or P waves, and secondary waves, or S waves. As you would assume, primary waves are the ones that happen first, and secondary ones are the waves that happen second. P waves push and pull rocks in the direction the wave is traveling. They compress and then release, and they can go through all types of materials. S waves kind of go back and forth. They move at 90 degrees to their direction of travel, and they can only move through solids. So they won't go through the liquid core of the earth. I feel like all this will make a lot more sense if I just show you a video. Here's a static diagram, but it's not as helpful as these videos. So let's take a look at the first one. That's it. That's a P wave traveling through a solid medium. Here's the second one. Oh, do well. So I'm hoping the difference between the P waves and the S waves is obvious. So the P waves are the ones that always arrive first at the seismic station. The farther the seismic station is from the source of the earthquake, the greater the separation you'll get between your P waves and your S waves. So here is an example of a seismograph. At some point, there was an earthquake that happened off the west coast of northern Sumatra. It took a while for the waves to reach the seismic station. And the first waves that reach or get there are the P waves. So that's when this first shaking starts. Then there was a little bit of a lag before the S waves started. S waves start here. So this lag between the P and the S waves can be seen in the seismograph. Lastly, the last waves to arrive will be the surface waves. And the surface waves are those ones, again, as I mentioned, that are most destructive. So there's a lot of information to be gleaned from a seismograph like this. You can eventually use it to calculate how far away the epicenter was and the magnitude of the earthquake. Let's look at how. Seismologists have made curves to help us determine how far away the epicenter is, and you can use them if you know the difference in the arrival time between the S waves and the P waves. So curves like this are used to determine how far away the epicenter is from the seismograph. Then we talk about the magnitude. There's a couple different scales that have been used to talk about magnitude of earthquakes. The modified Mercalli intensity scale is one of them, but this one is based on the effects of the earthquake. For example, that earthquake in Idaho that I mentioned earlier was between a 6, a strong, and a 7, a very strong. So these have effects like felt by all, many frightened and run outdoors, or difficult to stand, broken furniture, etc. But the scale might be a little biased. For example, if there's no people around to feel the effects, then we have nothing to compare to. If the area is not very populated, or if things are built really strong, then you can't really tell how destructive the earthquake might be. So because it's based on effects, it might be a little biased. The scale that's used more frequently is the Richter scale, and this is based on the magnitude, the amplitude of the largest seismic wave recorded on the seismogram. It uses the logarithmic scale. So an earthquake that's a 5 is 10 times smaller than an earthquake that's a 6. Okay. I feel like all of this makes a lot more sense once you try it yourself. And there's actually a pretty cool, though it seems kind of dated, tool that you can use to virtually determine where the epicenter and the magnitude of an earthquake is. What you're going to do, head to this website here. And when you do, be sure to choose the virtual earthquake thing located at the very bottom, not the new one. The new one's kind of lame. Read through all of the website and complete each step as you go through. When you've finished, they'll give you the option of completing a certificate and send that on to me. I'll count it as an assignment. Okay, guys, have a good day. We'll talk to you later.